Okay, here we go. All right, here we go. All right, welcome to Special Relativity 1, part of Physics X, Extraordinary Concepts in Physics, being taught at Michigan Tech. In this course, we're going to review some of the coolest concepts in physics. This is an actual course being taught at an actual university with no textbook required. If you want to know a lot more, please go to the first lecture in this series, and I'll have a lot more to say there. So today we're going to begin with special relativity. Special relativity is really cool. It's something I've been interested in for a long time, since I was a undergraduate physics major. It was something I've always been interested in. I remember I wanted to do research in special relativity until I realized that there isn't a lot of research done in special relativity anymore. But anyway, I'll be reviewing today key postulates and formulas, time dilation and the Feynman light clock, length contraction, and the famous E equals mc squared and mass energy equivalence. And I'll be asking a bunch of interactive questions, which I will start with. So let's say there's a flashlight. This flashlight is on and you move away from this flashlight. How fast do you see the photons from the flashlight move? So you have a flashlight, photons moving away from the flashlight. Now you're moving here. Here's my stick figure. And you're moving away. How fast do you see those photons move? Do they move slower than when you're not moving? Do you see those photons move slower? Do you see them move the same speed? Or do you see them move faster than when you're not moving? Well, I'll give you a second to contemplate. If you really like contemplating it, click pause when you're watching this and then think about it for a while. But I'll go quickly and say that the same speed when you are not moving. All observers measure the same speed of light. All observers measure the same speed of light is possibly the most fundamental and profound experiment in all of physics. It is strange and bizarre. So it doesn't matter. Someone could be moving that flashlight left or right. You could be moving back and forth at a fast speed. You're always going to measure the same speed. Light always has the speed of c. It's the maximum speed anything can go to. It's a profound concept that underlies all of physics. It was first discovered, about 105 years ago today, 105 years ago, and it's just tremendous. And it is the basis for having time being different between people, lengths of time, distances being measured differently. It's just incredibly profound, simple and profound. Okay, so now let's say a person passes you at 0.9 times the speed of light c. And they report that they're launching a person further moving 0.9 times the speed of light relative to them in the same direction. Roughly how fast do you see that second person move? So there's someone zipping by here really fast, their magic carpet, and then they launch somebody that's moving relative to them at 0.9 c. Is that 1.8 c? Is it just 0.9 c, or is it just below the maximum speed c? So think about that for a second. Click pause if you have to. And the answer is just below c. So there's nothing you can do to impress your boyfriend or girlfriend by driving your car faster than the speed of light, saying, I'm really going to press on the accelerator this time. I'm going faster than light. No, you can't do it. He or she will never measure you going faster than the speed of light. Speed of light is the maximum that information can transfer, the maximum that physical objects can move. They can't move faster than c. One of the greatest achievements in humanity, in my opinion, is understanding this extremely strange fact that there's a maximum speed limit. Okay, so some background on special relativity. C, speed of light in meters per second. V is the speed of something moving. L, which would be length. L prime, length measured in the moving frame. So L is in the proper frame, which is the rest frame, proper length. In your frame, time in seconds, time t prime measured in the moving frame, and m0, which is mass in kilograms, proper mass measured in its rest frame. Some background. So some history, as you might know, Albert Einstein did most of the heavy lifting in figuring out special relativity. Historians believe that humanity would have come up eventually with special relativity without him, but it was still tremendous that he did so. And it was a tremendous jump to say there's a maximum speed limit, and it applies, universally. It's also based on the principle of relativity that basically you can't tell if you're moving. If you're on a completely smooth train and you don't feel the bumps, you don't know, and you close all the windows, you don't know you're moving. You don't know. You throw a ball up in the air, comes up, comes down, you don't know you're moving. So there's no way to tell you're moving at constant speed. And that's the principle of relativity, and that's important that underlies special relativity. And then as I keep repeating, the invariance of the speed of light is key. Everyone measures the speed of light locally to be c. If you want to start doing complicated problems in special relativity, you have to be very careful. You can easily make blanket statements, but they're unlikely to be correct unless you identify specific observers that you're talking about. Identify specific frames of motion, which means trains may be moving at some velocity. Specific experiments. It's hard to make blanket statements without making something very specific in experimental idea. Another is what specific observations were you referring to when you measured that? If you get all of these, then it'll be easier to argue with somebody, because many times arguments involving special relativity, they don't have one of these things exactly right, and then it turns out there was a disagreement between reference frames or exactly what the experiment was or what specific observation was being made by what observer. Okay, so simultaneity also was called into question. Here we go. A train passes you. You touch a person standing in the middle of a train car, right in the middle, causing a spark. This spark has light. Do you see light from the spark hit each car end simultaneously? Yes, you do. No, you don't. Only if the person on the train does. Or doesn't anyone care if the train catches fire? So this is okay, well, you can stop it, go right to the answer, and the answer is no. You actually will see, standing on the platform, you actually see light hit part of the train car, the end nearest you. So if you started here, here's the train car, and here you are, and here's the person on the train car. They should be in the middle. They will see light, I'll put them in the middle, they will see light hit both ends of the train car at the same time. But further down, as time goes on, you're here. You're here, and you see light hit the back end of the train car. The train's moving like that. The back end before it hits the front end, because you're closer to the back end. So light hits it and then hits you. But to hit the front end, it has to go all the way a little bit further, and it has to come all the way to you. It's further. So if speed of light was infinite, it'd be the same, because infinite can travel. But since the speed of light is finite, it takes time to do things. And that breaks the principle of simultaneity, which means that not everybody's going to agree on what's simultaneous. The person standing on the train car will say, no, the light hit both ends of the car at the same time. And you'll say, no, they didn't. They hit the one end nearest me first and the other end second. It's different. And other people will think that it hit the other end of the train car first. So what you consider simultaneous depends on what's going on, depends on where you are, the reference frame you're in. And so that simultaneity is no longer something everybody can agree on as a profound concept that results from this. And here's a picture of a train car. I'll skip this a bit and go right to the next one. So Einstein understood this involved that in order to make all this work, in order to make the speed of light the same for everybody, you're going to have to drop some really fundamental concepts that people thought were the same, which is time intervals. People will no longer agree not only on simultaneity when things happen at the same time, but the length of time it took for things to happen. People now disagree on, and that's called time dilation. Richard Feynman quantified this well in something called the Feynman clock, where he would say, okay, look, speed of light, you have a light clock where light bounces up and down, photon goes back and forth between a light clock, and you're at rest with that. Now, move that light clock in this direction. And light will still continue to bounce back and forth. Oops, okay, wrong way, this way. It will still continue to bounce back and forth on the light clock. However, the speed of light is the same. So the time interval it takes to go from here to there is different. So you now disagree with an observer. The two observers, one moving with the light clock and one not moving with the light clock, disagree on how long it takes light to bounce back and forth. And that's called time dilation. Typically, when you see someone else move, you think that their clock is running slower. But when they look at their own clock is always running at the same speed it's always moved. So you don't measure your own clock as changing, but you can measure other people's clock as changing, and usually it appears to run slower. So here's another quick quiz. So let's say you have a particle that takes 2.22 microseconds to decay. Now another particle that's just born zips by at light speed, near light speed. How long do you measure for this particle to decay? Would it be less than 2.22 microseconds, the same as 2.22 microseconds, more than 2, or should you just be happy that it's not 6.66 microseconds? So you can stop the video and think about that, but I'll jump to it because I'm limited. The answer is more than 2.22 microseconds. And this is a direct result of special relativistic time dilation. You see time running for that particle, which happens to be a muon, run slow. So it seems to take longer. And we've seen in the lab, due to cosmic rays, things take longer than 5 times that amount. So cosmic time dilation works. It's the way reality is. People don't agree on how long it takes for things to happen. And that depends on how fast things are moving. Fundamental concept in physics. So if you take light and you move it along that duration of time, you can get length contraction too. And length contraction can be really interesting and messy and come up with lots of paradoxes, which we will cover next time. Because the strange thing about relativity is if two people are moving, each one thinks the other one is length contracted. And length contracts in the direction of motion. So how can both be right? And that leads to some really delicious experiments that you can do, and thought experiments that you can do that the answers aren't always obvious. So let's now jump to the most famous equation in all of physics, E equals mc squared. So this is really interesting because it turns out that in terms of rest mass, E is equal to mc squared, where m is the mass in your frame, and you get this strange thing, square root of 1 minus v squared over c squared, which when v becomes equal to c, when some small object begins moving really, really fast near light speed, that object, assuming it had mass, its mass becomes much, much larger. Officially, it diverges. So you can take anything. You can take a little flea and zip it up. If the flea could move that fast, it could be more massive than a bowling ball when it hits you. Mass, energy, and momentum all increase with speed. Okay? And now we'll go to one interesting aspect of this that I've always appreciated, not always, but come to appreciate when I saw it, is that total energy is not equal to kinetic energy, which is the motional speed. So the kinetic energy is the total energy minus the rest energy. So if you expand this, you can get the kinetic energy in terms of the rest energy here, m0. m0 equals rest energy. I think I defined this in an earlier slide. And you can do an expansion of the square root of 1 minus c squared over c squared and say that kinetic energy is equal to mc squared times this long line of things, which never ends. It's not important. But what happens is you can cut off the later ones and come up with the idea that kinetic energy is equal to 1/2 mv squared, which we know. So every time in introductory physics you keep learning E equals 1/2 mv squared. But here's what they don't tell you. There's a relativistic correction term. There's actually an infinite number of them. And the first one is 3/8 m0 v to the fourth c to the fourth. So E, kinetic energy, it turns out, is not just equal to 1/2 mv squared. That only works when the velocity of the object is really small compared to the speed of light. Once the things start zipping up there, then you have to start including the higher order terms. And they're always there. They're just not very dominant. So E is is only an estimation equal to 1/2 m, where m is the rest mass v squared. The first correction term is 3/8 m v to the fourth over c to the squared. So that will sum up, that will end this special relativity 1 lecture. And please remember to keep Schrodinger away from your cat. See you next time.